So we're continuing right now to the state-of-the-art session. My name is Eran Toch. I'm a faculty member here at Tel Aviv University in the Department of Industrial Engineering. I'm the co-director of the IWIT lab, the Interacting with Technology lab, and my main work is on privacy, how it affects people and how people manage and affect it back. In this short talk, I'm first going to present a little bit about the state-of-the-art of big data right now. I'm going to kind of weave the other speakers in the session to my talk. Tamir Tassa from the Open University, Aline Attias from the Ministry of Health, and Nahum Kiryati from the Faculty of Engineering. And then I'm going to present a short study that was done in my lab about genetic privacy and try to kind of use that as a case study for really the ethical challenges that we face with big medical data. So a little bit about the state of the art. And to understand where we are right now, we need to understand a little bit about the history of big data and how this buzzword came into place. So when I think about how did we get here, I'm thinking about four processes. Some of them technological, some of them organizational, some of them are kind of a mixture between the two. So the first really is the dropping price of storage. So, 1 gigabyte cost about $1 million in the 70s. Now it's, kind of a hundredth of a cent. So the price of storage has dropped immensely. It's now, it actually costs more money to delete data than to just, put it in a hard disk and just forget about it. But you don't forget about it. When you keep the data, eventually you will use it. So with the dropping price of storage, we see more software solutions that are able to manage this data and analyze it. The latest is our techniques that come from parallel computing, like Hadoop, Spark, all those kind of buzzwords. But basically, those are large clusters of computers that can do large-scale parallel computing and eat all this kind of data. So the second advancement is in the advancement of analysis methods. So there's in the last, I would say, 20, 30 years, we see many changes, many developments, especially when we analyze non-parametric data which is not necessarily numeric, things like pictures, text, unstructured data which isn't normal, doesn't follow some predefined distribution. And the latest buzz is, for example, deep learning. So Nahum Kiryati is going to talk a little bit about it, but basically, you can think about deep learning as a way in which you can analyze the unstructured data, not using one big model like what we used to do a couple of years ago with one linear regression model or one simple model, but with millions of different models that can classify, for example, pictures. One example is a company here in Israel called FDNA, founded by one of the co-founders is Leo Wolf from the School of Computer Science here in Tel Aviv University, in which they use pictures. We use a huge number of pictures of mainly children to identify genetic diseases, genetic problems, just from how the face looks like. And they outperform doctors when they do it. So again, Nahum is going to talk a little bit about using deep learning to X-ray. The third technological change is the falling price of sensing. So now it's much cheaper to install a sensor, a camera. It's much cheaper to analyze blood tests. It's much cheaper to analyze the genetic information, of us. The first genetic sequence in 2001 cost around $1 billion. Now the price of full genetic sequence, I'm not talking about the 23andMe, but full sequencing drops below $1,000. And right now, full genetic sequencing is becoming a test that people with oncological challenges are doing, and we see that it's much cheaper now, much easier to accumulate the data. The fourth change is organizational. So we see that companies, organizations, government change, sometimes because of big data, sometimes this kind of change predicts the use of big data. So just one example, organizations are becoming larger. So we have the number of HMOs in the US and in Israel is becoming smaller. You have more and more huge HMOs, which have access to huge number of patients and tests. We see organizations like the Cochrane database of systemic reviews, something in the medical world. I hope that I pronounce it right. Probably not. In that, that take the databases of results and then analyze them to create systematic reviews and recommendations for doctors and practitioners. So we see many types of organizations that create this kind of a pipeline of big data, the collection of data, the analysis of data, and then creating knowledge out of it. So what we see, and we see it in many different places, but I think the medical world is a leader, is we see an economy of big data. So there are more and more people that go and learn how to use big data. We have in the Department of Industrial Engineering, we have a new program in analytics, for example, that gives people tools to do that, and students are very interested in that. That means that you have more people that can do the analysis of big data. You have systems that make big data cheaper to store and to analyze, processes that take that into account, those government initiatives that Aline is going to speak about that try to solve and create a centralized repositories or some centralization of the data. And we have this economy growing. And of course, if the economy will work okay, if things will move, then we can get amazing things out of it. And we just had, in the last session, we had a couple of examples of the amazing things that you can do with big data. But of course, the problems in big data are inherent. They're not something new. We have to tackle them from the start. And we heard, a lot of problems in the last session. And now in this session, I think we're going to especially talk about privacy and openness. So these are two very different types of problems. So in privacy, you have a threat about what's happening when the information about people, individuals, is collected. What types of harm or changes could happen to them because of that? In openness, you have almost the exact opposite. What happens if the data isn't open? What happens if researchers, organizations, sometimes even people don't have access to the data? So I'm going to very quickly present a study that was done in my lab, that is an interesting, I think, case study for these types of problems. So this is a study conducted by Netta Reger, a student in my lab. She was co-advised by me and Professor Noam Shomron from the Faculty of Medicine, and she looked at the privacy threats of genetic information, especially full sequencing information. So one of the things that she's done, she took full sequence information of 420 people taken from the PGP and 1000 Genome Project. And she tried to calculate, she done some text analysis, went to online papers, online databases, and tried to calculate what are the possible harms that can come to people. So for example, she calculated what happens if the HMO, if the insurance company would get knowledge about the full sequence information, and let's just pretend that they don't have any legal or any other types of regulatory framework that prevent them from using this information. So for example, for 25% of the people, the premiums would go up by 80 to 100%, okay? Because the HMO will learn something new about the probability of them having cancer, diabetes, lots of diseases and problems that can be predicted these days from full genetic information. Now, maybe in the long run it will be okay because the premiums of other people will go down, but we don't know. So that's, I think, a very concrete example of the bad things that can happen if information about you is leaked. So if you sign to 23andMe, or if you do full sequencing and information stays in the hospital, and then Maccabi puts its hands on it, then presumably, if there's no regulatory framework, a rational health insurance company would perhaps jump up the premiums, perhaps. Another interesting finding is that people from South Asian descent will see the average of their premiums will go up by 20%. People from African descent, African Americans and just people from African descent, will have their premiums go up on average by 100%. So we try to understand why is that? Are people from Africa, have more diseases, genetic diseases than people from Europe? The answer is no, they don't. The reason is that in genetics, when you try to see if something predicts a disease, you look at the mutation, and the mutation is calculated in relation to the baseline population. So the different ethnic groups have actually very different DNA. So if you compare it to the average population, you would get nowhere, and everybody will have a mutation. But if you compare it to the baseline population, then you can get a better grip of what is a mutation and what is not. And there are less people who had their full DNA sequence from Africa or from South Asia. Most of the people who had their full sequence are from... No, I'm sorry.
I can't take it anymore. There's just a lot more genetic variation
okay,
in Africans than in Caucasians. So
that's actually an open question. There's a paper in Nature about this.
So actually,
But even if you can't take this anymore, can I please ask you to take it just...
No, I think it's not fair. What it means is you're interpreting genetic variation as being a mutation, i.e. having a negative effect. So that's a problem in your algorithm, not in your
But we were able to show that there's a sampling issue here also. Okay, so if you have a bigger sample, okay, and if you have larger variations, but you still have a bigger sample, then you can overcome those kinds of things. I agree, by the way. But again, I think it's when we talk about big data, we want to talk about what sampling means. And here we have kind of an opposite problem in which if the sample is too small, if you don't have enough information, then you can actually harm. There are consequences to the people who have this kind of information. So we have openness and privacy sometimes working together, sometimes they conflict. It's a weird world. So for the rest of the session, we're going to change the order a little bit. We're going to first have Tamir Tassa from the Open University talk about the state of the art of anonymization. Then we're going to have Nahum Kiryati from the Faculty of Engineering talking about, I think, mainly kind of challenges to openness in X-rays. Am I getting it right? See? Sort of. Yeah. Okay, and then Aline Attias from the Ministry of Health will talk about what the government can do with this very baffling situation. Okay, Tamir.
Okay, so thank you, Eran, for this very clear introduction, and thank you, Michael, for inviting me and having this important day. So, as Eran said, we have tremendous amounts of data, of personal data that is collected and can be analyzed. We have fantastic data mining tools and softwares that can be used to infer trends and patterns. So let the party begin. But as we know, the party cannot just go on wildly without any limitations, because the use of data that contains personal information has to be restricted in order to protect individual privacy. Now, it's been known for a long time that naive de-identification, namely just removing identifying attributes like name or ID number and so on from the data, is not enough. Tanya Sweeney from Carnegie Mellon at the time, now from Harvard, she showed 18 years ago that about 87% of the US population can be identified by the combination of supposedly naive attributes like gender, zip code, and date of birth. And therefore, more aggressive techniques should be applied on the data before you release it for scrutiny and for analysis and for research. And the first formal privacy model that achieved widespread visibility was Anonymity, that was proposed independently by Samorati, Pierangela Samorati from Milan, and Tanya Sweeney. around 1998. This is a very, very basic model that suggests to distinguish between attributes in the data, which are so-called quasi-identifiers in the sense that also adversaries can get hold on them. So let's say my ethnicity, my age are attributes that possibly adversaries can get hold of, and other attributes which are sensitive and cannot be can be learned by an adversary. And the idea is to generalize, to replace accurate, exact values in the let's say in the age column or in the zip code column by more general values, so that each row in the data in the database will become indistinguishable from at least few others, k-1 other records, and therefore if an adversary will try to locate my record in the database, he will be able to track me down only to some subset of records, but not less than that. Over the years, it was shown that this is not enough, and other models which all share letter hyphen word title like L diversity, T closeness were proposed. In all of them, the data is manipulated usually by means of generalization until some syntactic condition is met, and then the purpose of this is to reduce the risk of performing what's called linking attacks. Now, until 2006, many people dealt with those questions and with those methods. Many publications, many serious people, but to the best of my knowledge, none of them was a cryptographer. And then in 2006, it was a very nice day in Venice, in ICALP conference. I sat there in the second row. Cynthia Dwork, who's a very prominent cryptographer, presented differential privacy, which is a much more rigorous notion of privacy, which is based on adding noise to database entries. And the idea is as follows. You make no assumption on the adversary in the sense that you assume that the adversary is almost God. He knows almost everything. The only question that he does not know is whether Eran's record is in the database or not. All the rest of the record of the database is completely known and open to him or to her. And then you want to add to queries, to answers to queries, some level of noise, so that this adversary will not be able to infer from the answer whether Eran's record was or was not in the database. And there seems to be a widespread belief that differential privacy is immune to all the attacks that were devised against the methods of anonymity, and that it renders those models obsolete. It is very, very clear in the academic arena, where if you look at the papers that are published, then starting from 2006, less and less papers are accepted and published on the classical methods of anonymity, and more papers are published, a great number of papers, on differential privacy, and in some sense it even looks like a deus ex machina, a silver bullet, and the ultimate solution. And I want here to give a somewhat more cautious understanding of this. I think that as promising and rigorous and mathematically sound this notion is, it is still not ripe to be adopted in practical applications for many reasons. The first reason, philosophical reason, is that since this notion was developed by cryptographers who put privacy in the center, then it places the question of individual privacy as the most important one, but it tends to forget that there is also a different leg, a different reason for this, for all this thing, which is the right of the public to learn trends, to learn something about ourselves. And if you put all the focus on privacy, perhaps you are damaging the ability to learn. And then what's the point of all this? So it's definite that the anonymity methods provide inferior levels of privacy. There's no question about it. But the question is this enough to finish and state that those methods are obsolete or not? And I think not. And I think that societal practice and laws such as HIPAA, for instance, in the States, recognized that the right to privacy must be balanced against the public good. Now, there are several issues that make differential privacy still not entirely ready to be adopted in practical systems. And by the way, I'm not aware of any practical system that, especially not in the medical business, that adopts differential privacy. So very, very quickly, because I don't have much time, one of the problems is that differential privacy...
You have 4 minutes.
4 minutes, wow. So that was wow from the under, not from the... differential privacy is more designed to interactive models in which the hospital keeps custody of the data, does not release it. It's not a release and forget. You keep and you respond to queries on the data. This is definitely not suitable for organizations like companies, like hospitals, like HMOs, and so on. They don't have the expertise to do data mining. They want to release and forget. This is not suitable for interactive settings such as that. But the more important problem is that the noise which is being added to queries answers makes the answer not reliable in some sense, because you never know how much noise was added. And we all know the story about the person that drowned in a pool in which the average depth is only 1 inch. But of course, if there's one place in which it's 3 meters deep, then you can drown and die over there. And therefore, in medical business, I don't think that medical researchers would like to accept data in which values were completely distorted. And in Usenik Security Conference 2 years ago, the best paper the best paper award went to a paper which was called Privacy in Pharmacogenetics. Yes, and they tried to analyze the applicability of data of differential privacy, and I quote: "We find that for privacy budgets effective at preventing attacks, patients would be exposed to increased risk of stroke, bleeding events, and mortality. We conclude that current differential privacy mechanisms do not simultaneously improve genomic privacy while retaining desirable clinical efficacy." And so this is something that should be kept in mind before adopting differential privacy-based solutions. There are many other issues that I don't have the time to go through. But I think that the main message should be that syntactic anonymity models substantially reduce privacy risk if you compare it to a release of actual data values, and they provide guarantees on the correctness of analysis which is based on anonymized data. And in many cases, this is preferable to adding noise, because adding noise, as I said, removes the certainty about how correct the data is. And a very good study that was presented in ICDE 4 years ago compared the privacy and the utility that is provided by 3 models of anonymity and differential privacy. And they concluded that, first of all, the difference between the privacy guarantees is not as large as data privacy advocates believe, and that in every setting, the risks should be evaluated, and then the choice of the mechanism should be made based on the risks and from adopting this or that privacy-preserving mechanism, and therefore all methods are still viable, are still relevant, and the challenges that the problems that occur in all of those paradigms and methods should be viewed as opportunities for future research, and not for calls for abandoning this or that method. And there are calls in the research community to abandon the research of anonymity. And in practice, I believe that this should be taken very, very gravely into consideration. And to finish with an optimistic view that I quote from the last sentence in a paper that we published on this, Professor Chris Clifton from Purdue and myself: "Advances in both paradigms are needed to ensure that the future provides reasonable protections on privacy, as well as supporting legitimate learning from the ever-increasing data about us. Thank you very much.
Okay, thank you. Nahum?
As you wish. Can you please get the microphone for the okay?
My name is Nahum Kiryati. I'm from the School of Electrical Engineering here. I work on image processing, computer vision, and in recent years on medical image analysis, which probably brings me here. And also quite recently I graduated from this law school here, and I can say that I've learned from the best because I've taken courses with both Michael and Shai, which were very good. In medical image analysis, that means computerized medical image analysis, I can generally say that we have two big classes of problems. One problem is image enhancement. Image enhancement means you have a poor quality image, you want to make it better in some sense. For example, we take CTs of people. We have a radiation hazard. We want to reduce the radiation hazard. In order to do that, we want to reduce the level of radiation. The outcome is that we get a very poor image from which we cannot learn what we need to learn. Similarly, we want to put an MRI machine inside the operating theater. Problem, high magnetic field. So we want to reduce the magnetic field, but if we reduce the magnetic field, we get a very poor image. So it would be a good idea to improve the image, so we'll be able to put a low magnetic field MRI machine in the operating theater. Third example, we want to take an MRI of the brain of a fetus inside the womb. Problem, the patient is not cooperating, it's moving all the time. So we get a blurry image. Question, how do we get a good image of the fetus brain, of the moving fetus brain, from this kind of MRI? That's another example of an image enhancement problem. Now, the second large class of problems I will call classification and segmentation, and that means once we have some image data, to automatically identify, delineate organs or conditions. For example, if we have a patient with multiple sclerosis, MS, doctors tell us that we want to sometimes track over time the lesions in the brain. So it would be really nice to have a device that will delineate, segment, and track the brain lesions over a sequence of MRI scans. For example, in CT, we may want to detect abnormal lung nodules that pose risk for lung cancer. So it would be very nice if we could have a machine automatically take the CT image and detect the suspicious lung nodules. Another example, brain tractography, that is figuring out through a special type of MRI how the brain fibers go in our brain. If we will be able to do that, automatically it will really help in neurosurgical navigation. The surgeon will know exactly how to maneuver inside the brain, causing minimal damage. In terms of this scientific field, there are several routes. One of them is the image acquisition route. We have CT since the 70s, MRI since the 80s, and then lots of other techniques. And then the other route is image processing and computer vision, evolving really since the 70s. And these two fields, the acquisition and computer vision, came together roughly at the early 90s. Since then we have dedicated conferences, for example, on medical image computing. So this is a nice story, and then the revolution comes, the disruption. The disruption comes at 2012, and it comes generally in the field of computer vision. Some people come with a technique that is, they called it convolutional neural networks. It doesn't matter. Now it comes under the more general title of deep learning. So there is this new technology that creates a dramatic revolution. For example, face recognition, the ability of a computer to recognize a person from his image, is known to be a very difficult, challenging problem, more or less until 2012. I can tell you now, just 4 years after 2012, that computers do it better than people. Computers do it better than people now. Deep learning is really changed the field, and it changes the field all the time. And the issue with deep learning is that it requires massive training data. So in order,
you tell it to Shikri, the biometric database.
Perhaps. I'm not familiar with the biometric tricks, but I'm looking at it from the medical perspective. So if we want to have an algorithm that will do something nice for us, like the things that I've told you earlier about, we sometimes need millions of annotated images, or hundreds of thousands of annotated images where the doctors added some explanations, and perhaps we need some metadata, the same kind of metadata that the privacy people want to anonymize so much. So all the previous approaches are obsolete now, and if we want to do something useful, we need these millions of annotated training images. Now, the public good was mentioned here as a balancing factor, so I would just want to exemplify a recent work that we presented just a couple of months ago. We are working with City, and we were asking ourselves how much can we reduce the radiation and have the radiologist still detect a suspicious lung nodule. So we have been able to show that with nice image enhancement algorithms, we can reduce the radiation by 94% and still allow the radiologist to detect the suspicious lung nodule. Now, of course, this is not a medical technology in practice and so on. This is just giving us a roadmap, but it can tell you that if we follow this route, sometime in the future, we will be able to have incidental detection of lung cancer in CT. So, for example, when someone comes to do CT for another reason, say to check his whatever inside, the machine in its own free time might go over the scan and say, in addition to all your problems in the colon, you also have a suspicious nodule in your lung. This is a dramatic benefit. It is a dramatic advantage.
This is a good question if it is a benefit.
Right.
Okay.
See, the low
At least
ones
it's
are also
Too early and you don't know what is the outcome, and you try to start. I'll give you an example of the TSA that we did to discover prostate cancer, and now we realize that it's bullshit.
Okay, I will leave this kind of decisions to the doctors. My business is to provide the technology that will allow you to contemplate on the possibility, its advantages and disadvantages. Another issue is once we can reduce the CT radiation levels so much, people might consider using CT for lung cancer screening. That means radiating healthy people, the general population with X-rays, because the level that we need will be so low. Now, if we want to do all these wonderful things, the only question is where can we find millions of annotated medical images? And for most researchers like myself, because Maccabi will be ready just in only in the first quarter, you said. At this time, the data is available in the hospital picture and archiving communication system, which we call the PACS. So all the data is in the PACS, and the question is who can access the hospital PACS?
Who owns it or who manages it? Is that
the hospital.
And every hospital, you think that the hospital is about the doctors and the patients. It is actually about a big computer called the PACS, and everything revolves around the PACS. That's the...
Only the pictures. The picture archiving.
Yes, but if you consider the volume of imaging data that is acquired every day, you get it is formidable. So every major hospital has its PACS, and the question is who can access the hospital PACS? So there are, of course, there's the first question: who is allowed to access the hospital PACS, but I'm asking who can access the hospital PACS. So the people that can access the hospital PACS are hospital doctors. Now, hospital doctors have their own agenda. that is usually totally unrelated to my agenda. Many of them are unaware of the R&D value of the data in the PACS, and most of them are not technologists, so most of them cannot do the R&D themselves. So this is one class of people with access to the PACS. The other class of people that can technically access the PACS is people that make scanners or sell the PACS itself. So they are not supposedly, they cannot legitimately access the data, but in practice they do. So they, like scanner manufacturers, are very interested in techniques to improve scanning results. So technologically they have access to the PACS. They are interested, they are aware of the value, but their access is informal. So there should be Chinese walls separating them from patient data, but they are responsible for maintaining the Chinese walls. So, and then there is the community that cannot access the PACS, and that is myself. As a representative of the general research community, I don't have access to the PACS.
And the Chinese hackers that can.
Yeah. So there are, of course, fundamental obstacles to providing access to archived medical images. So one is identifiable data, so we talk about anonymization, but anonymization is often limited. Once we sufficiently anonymize the data, it often loses its value. Once the metadata is gone, once we introduce differential privacy that actually ruins the data for us, and so on. Then there are ethical issues like confidentiality, the fact that the image was acquired for a particular medical purpose, and now we were talking about opt-in and opt-out, but most of our data is legacy. These are images that have been taken for other purposes years ago. So the patient did not have a chance to opt in or opt out or even know what's going to do. Then there are patient concerns. Sometimes you'll ask the patient and the patient will say, I'm not sure. For example, ladies, will you agree to share your mammograms, your colposcopy images? And gentlemen, if any of you had gone through transrectal ultrasound for prostate cancer, will you want to share this kind of data? And there's the legal framework in this country. In this country, there is privacy protection law and patients' rights law, and other countries, HIPAA and so on, that also, all the current legal framework as a non-expert, from my point of view, worries more about the interests of the specific patient rather than the interests of the general community that includes the specific patient. So the current state of affairs in my business, which is medical image analysis, is that I don't have access to big medical data that I need to do all these things. The research is limited to a small number of major hospitals, and there are big names worldwide like MGH in Boston, for example, or other hospitals of this scale that have the facilities and the ability to do this kind of research that involves technology and medicine. Large corporations, for example, GE, Siemens, and other vendors of, say, MRI scanners, have better access to data than small and medium enterprises. Independent academic research in this field is practically impossible. So I take pleasure in collaborating with several major hospitals in this kind of research, and I'm fortunate to enjoy this collaboration because I don't have any choice. I cannot get the data without...
You should have studied medicine instead of law, and then you would have access to the other way.
And then there is an interesting sociological effect. There is, I would say, anecdotal evidence, but we are all familiar with these anecdotes, that hospital personnel often act as data brokers. They have access to the data, they are not sure what to do with it, but they know that there are other people there that are after this data very diligently. So some contract emerges in which the necessary data goes from the PACS to the researcher through the hospital personnel for some benefit. So just one last minute, I'm interested in uniting the medical image analysis researchers with their data, democratization of research, removing bias against academia and SMEs in the current system, and there are legal, ethical, and technological solutions that could be considered, and thank you very much.
Thank you.
Thank you, Nahum, and now Aline Attias from the Ministry of Law.
Hello, everybody. I think by the end of my...
Thanks.
Thank you. I think that by the end of our talk, you'll understand why we decided to switch. I'll be the last speaker in this session. Thank you for hosting me. I'm Aline Attias, head of the platform that we are building now in the Ministry of Health, big data research platform. My background is in information system engineering, both from the Technion and the Boston University. This platform that we are currently building, it's under construction. It will be in production in the first quarter of 2017, is one of the spins of Digital Israel, which is a national initiative that wants to get the leverage of the digital age for the benefit of our citizens, meaning that the citizens will have a better service from the government, faster, smarter, better, equitable service. So what we are currently building is a technological platform that will allow diverse data sources connection in our platform, and once the data is transferred to our platform, we'll do the binding of diverse sources and then do the identification. Only on the transferring of data it will be open, but by the time it gets into the platform, we'll do the identification, as mentioned before, of identifying fields and quasi-identifying fields, and they will be masked according to their type and potential use. Meaning, I don't need the first name and last name of the people involved. There's no research utility for that, but I will have to know some demographic features, but depending on the research we want to do, the identification will vary. The idea is, of course, to lower the risk of detection of private information while allowing public good by doing medical research. One who wishes to do research, a big data research on medical information, will define the data set that he wants to use from our catalog. Once he defines it, he goes through a process of approving, which is now also discussed and defined in the Ministry of Health. The approval will include ethical issues, security issues, purpose of use, and according to all this process, the researcher, the team that wants to research the data, will get a workspace that will have 4 components. The first one will be data tools, big data tools. We do mainly open source tools, but also others are allowed. Data tools to investigate the information. We'll have the data set defined at the beginning of the process for this endeavor, and we'll have data science services offered to the team that wants to research the data. We know that in Israel there's a lot of big data done, but less in the medical domain. So we help investigators, researchers learn about how to deal with big data, which is a little bit different than classic research. Also, we want to give the opportunity for new techniques and state-of-the-art software, so researchers could bring their own tool, and after clearance for security reasons, they can use their tool or their technique or their algorithm in our workspace. However, the workspace is disconnected from the outside world, meaning we'll put the data there, we'll put the tools there, we'll allow collaboration for the team of researchers, but they could not take data in and out. This will be done just through us for understandable reasons. What I want to emphasize, this is the offer. I want to take this opportunity to talk about two technical issues from an ethical perspective that we have in building this platform. Because building a big data platform is not so difficult. It's a complicated architecture. We use a lot of tools, but it is done here in Israel and all over the world. We have a specific issue dealing with ethical question, and one of them is the de-identification. I'm coming from the financial arena, and for me, what the data saved in the computer is the absolute truth. If my balance is 200 shekels and 20 cents, that's it. And even if the bank is wrong and it's not 200 shekels and it's 300 shekels, the fact that in the bank's computer it is written 200 shekels, it becomes the truth. There's nothing to talk about it, but as I understand, in the medical field, it's different. The doctors here will tell you that even if a patient is coded for a certain disease, gets medication for that disease regularly on a regular basis, it still doesn't mean that he has really this disease.
Sometimes in the bank I have 200 and 300. Inconsistency.
No, but the fact that the computer of the bank, I want to see how you go to the bank and said, well, I did the math and you are wrong. Most of the time it will be almost impossible to prove it, unless it's some kind of error that goes all over the clients of the bank, and if a lot of people will come, they'll see that they have a problem. But if only me comes and said it's something else, usually it won't work. Okay, so in the medical field, the thing is that the fact that I have the data, the exact data coming from many sources, it doesn't mean that this is the absolute truth. And of course, there's the issue of different procedures, different definition. It was mentioned before, a diabetes patient doesn't mean in Maccabi is not the same like the one in Clalit. It's not the same like the definition in the Ministry of Health. And if one wants a subset of data for diabetes research, I'll have to combine all these things and give some kind of definition. So the way that we intend to tackle this issue is by dealing and maintaining a lot of metadata. meaning understanding the sources we are getting from different providers and trying to maintain a clarity of what data is delivered for a research. Again, what we are doing right now, we are using a combination of K-anonymity, T-closeness, and differential privacy. We are trying to build something tailor-made especially for us. We are working with the R&D of IBM in Israel and abroad. We are working also with independent researchers trying to figure out a way to do it, because again, in medical research, the proximity is not good enough. You have to know the exact data, and for example, if I have one blood test of a patient, I don't have to know its demographic, name, ID, etc. I'll just use the data that I have, and I can identify it, and that's the thing we had to deal with. Okay, that's it. We are, as I said, we are doing currently just two sentences. We are doing already pilots on our data for natural language processing in Hebrew. It appears, as we know, most of the medical data is free text. So we're taking free text from all kinds of sources. And our next step, I hope by the second half of 2017, is go into the dealing with imaging processing.
Thank you. Thank you. So we have just 5 minutes for Q&A, so let's make it fast and let's start. Yeah.
So I think, Aline, what you said is really true. That dealing with medical data is very complex. And I'm doing, for example, now a study with Kira Radinsky from the Technion about hypertensive patients. And we get results that only by getting back to the files I can understand. Metadata won't help you here, because the metadata says it's a hypertension field. That's medication field. You can't do anything without it. That's why I think that you have to be very close to the data in order to be safe enough and understand the outcome that you have. Because in all my studies, I have to get back, and I get back to my patients to understand the outcome that we get out of the data. And that's why I think that it's a mistake to take the data to a central place, to anonymize it, and you can't go back to the data and validate the results. I think that it's a mistake, and people who do it don't do enough research to understand the mistake.
Can you break it into two and have the data scientists do whatever magic they do and come up with an algorithm or something, and then in a different research, which can undergo Helsinki procedures and informed consent and all of that, validate it or not?
From my experience, it's back and forth. So I do one step, I go back. One step, I go back. For example, with this hypertensive, every week we go back and forth, because they give me the results, the mathematicians. I say it can't work. Let's look at the patient. We look at the patient, we go back, we say it's not, we go back. You have to do it back and forth. And metadata won't help you a bit here, nothing.
Aline, do you want to?
Yeah, when I mean method, I agree. I also agree with everything you say. When I mean metadata, I don't mean the classical metadata that we know for other technical reasons. I mean, after you did on your own subset this cleansing, then you know the procedure, the definition that you want to use, and this is for me becoming metadata.
Yeah, but it's not a definition, because you see that physicians work in different ways, and it's very heterogeneous, and you have to get to be very close to the data. And Dan, you asked me why people want to be partners in the study. Because we saw that when we take data and give it to researchers, it doesn't help them. They don't come with good study to us because we have to go back and forth together. And we know, for example, if you look at glucose level, you see that in our emergency rooms, the glucose level is also always high. You won't know it from the database, okay? We understand the data. If in Maccabi we have a new rule, you don't know it. All of a sudden it changes the data. You have a new mandatory field, it changes the data. So you have to be very close to the data, the manufacturing of the data. It's very important.
Okay, other comments, questions? Yeah.
I would just like, my name is Daniel, I'm from the Ministry of Health. I would just like to ask that as far as I know, there are two kinds of researchers. One would like to, for example, look at high level of outcomes. For example, what would the average patient be like? Or how would the average patient respond to something? And this kind of research, you don't need the exact data about each patient as Varda is telling us over here. For example, in such a research as you did with the colon cancer, you really need to go back and see if the patient did something or does the coding mean something very specific. But I don't believe that every kind of research need this, I don't know, maybe exact details.
Okay, so I've done...
Okay. Yes, over there.
I have a question.
Can you please present
yourself? My name is
yourself?
Yara Shmueli. I just recently finished my PhD from Tel University, and I have a question regarding your platform. Are you going to take into account the private medical records? Because today, if I want to check the whole view, I have a missing all regarding all the private medical records and the private health insurance companies. So, are you going to take them into account in your platform?
Again, maybe I didn't say at the beginning, it's a voluntary platform. We're not going, as a regulator, say, all the data is ours.
Voluntary for the physicians or for the patient? Voluntary for the physicians or for the patient?
Voluntary for the researcher. Okay?
No, but who gives you data?
Giving the data depends on the researchers, meaning I have already, the medical institutions, and it could be a private company, meaning I am responsible to give back the research data anonymized at the level that will decide which is sufficient without damaging research utility. Meaning, if you want to do a research with a private company and the private company will bring her data, I will link it, de-anonymize it, and you could use it for research. Meaning, I'm not going to organization and saying, give me the data. That's yeah.
Okay. Sadly, we need to wrap up this session. Fortunately, there's a session about access to data later today, so you can have your fights then. Thank you so much for hearing us all. And
thank you. Thank you, Eran. And we are continuing directly to the next panel on ethics, moderated by Moira. I think it would be better if you come over here.